Hello everybody, welcome to second semester. You made it through half the year, you're halfway there. We're going to start off the semester with a topic that a lot of students like, which is gas laws. We're getting away from just drawing Lewis structures and back to a little bit of math, which a lot of students like. However, it is incredibly important that you do not forget the concepts behind how gases behave. One of the things we see is that especially honors and AP Chem students tend to fall back on their mathematical strength, and they tend to not study or think about the concepts behind gas behavior. And that can be a real problem, especially on things like FRQs, where you have to explain why something is happening. Or on multiple choices, you may end up wasting a lot of time trying to do the math, when in reality, all you had to do is think about the concept and you could have found your answer much faster. So this is mostly just a reminder PowerPoint of some of the topics, the conceptual things you should know. If this feels, like, oh, I don't really remember any of it, go back to the honors videos and refresh your memory. So remember that one of the things that's kind of fun about the gas law chapter is that it's a lot of real life examples. They'll talk about things like the pressure inside a container, or maybe you're taking a bag of chips up Everest and what happens to the bag of chips. So a lot of real life examples. We need to remember that gases expand to fill the containers that they're in. We say that they are fluid, they flow, they slide past each other. They have a very low density, very, very low. They're very far apart. Those atoms are spread out really far apart. Because of that, because there is so much space between the atoms, we say they are compressible. That's why we can get things like, oxygen tanks to go scuba diving. You can take a large volume of oxygen gas and squish it down really small. Some words that might be new to you that we'll learn during the chapter is that the effuse and diffuse. So these are related to how gases will mix and spread around and travel from one part of a container to the other. We'll learn more about that later. Sometimes people are so focused on the math that they forget to even tell me what pressure means. What is pressure? Pressure is caused by the collisions of the molecules with the walls of a container. The more often and harder that the molecules are hitting the container, the higher the pressure is. We can mathematically calculate pressure. Pressure is how much force is being applied to a certain surface area. The official units, right, those SI units are Newton per meter squared. That probably isn't familiar to you. That's more like what they would use maybe in a physics class. We often use things like pascals or atmospheres, millimeters of mercury, torr, kilopascals. You should remember your gas conversions, your pressure conversions. Yes, the AP Chem equation sheet has some, but if you're relying on looking at that every time, you are probably going to be wasting a lot of time. I would probably memorize the common ones. You learn in Honors Chem about something called STP. The thing is, I don't think it gets used very much, so sometimes people forget what it means. So STP is a standard set of conditions. Remember standard state? It's kind of like that for gases. So the pressure at standard would be 1 atmosphere, or 760 torr. The temperature would be 0 degrees Celsius. If you have a gas, any gas, doesn't matter what kind of gas, at standard conditions, it will occupy 22.4 liters. You can use that as a conversion factor to do a little bit of dimensional analysis sometimes. It can really speed things up. If you remember your ideal gas law equation, PV equals nRT, if you plug in the pressure and the temperature and 1 mole for your N value and you use your R value, you could calculate mathematically that this is true. Or you can just believe me, okay? You can just memorize it. Most of the teachers at our school, most of the chemistry teachers at our school have a cardboard box in their room that shows you how big 22.4 liters is. So maybe look around your classroom and see if you can find that box somewhere. Mine's up on top of the cabinets. So here's what I was talking about, where you can see if you rearrange your ideal gas law equation to solve for volume, moles times your gas constant, make sure you pick the right one, times your temperature in Kelvin, make sure, please, 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 I'm begging you, get good at making sure you're in kelvins, divided by your pressure. Make sure that you are picking the right R value based on your pressure units. That's a common mistake. I am not going to require, personally, I don't require that you show me all these units canceling. But if I ask you to demonstrate that they do cancel or prove that they cancel for some reason, you should be able to. But unit conversions are very common in this chapter. Be careful with your units. If you struggle with it, then put the units in and actually cross them out like you see here. It's better to take 10 extra seconds and get it right than rush and get it wrong. Now, in Honors Chem, you're taught that everything that you do, you're always going to pretend that all of your gases are perfect, that they all follow perfectly, perfect behavior, that they are not attracted to each other, that they don't repel, that they're teeny tiny particles that are called point particles that have no volume, that they're far apart, and all of that. Now, in real life, not all gases are perfect, but 90% of the time, they'll be good enough that we can do our calculations. But it is important that you understand that the difference between, for example, the ideal gas law equation and the real equation would be some correction values. We would have to account for the volume of the particles. We would have to account for whether or not they are attracted and repelled. We would have to account for the fact that they collide with each other and lose a little bit of energy. Things like that. Being able to describe why gases in real life don't follow perfectly our mathematical equations is important. Doing the math for the real gases, not something we'll worry about. College, yes. Here, no. We will see in later lessons how the real gases behave and how they deviate mathematically, but we won't have to do the calculations. All right, so if any of that stuff is unfamiliar to you, how gases behave, how pressure is, units are converted, how you would use molar volume, any of those types of things, that kinetic molecular theory about how the particles zoom around and, collide, any of that's unfamiliar, go back to the honors videos and watch those, okay? Hopefully that was a good reminder of some of the concepts from the chapter. Bye, everybody.